Okay, so how is everyone today? Good, I hope? All right, so last time we were talking about by parts. We've done probably enough of those for the moment. So now we're going to move to the next idea. And one of the before we move to it, I want to just mention something because when I did something in lecture last time, I got a lot of unsure looks from you. So we're going to review something a little bit and then go to a new topic. So to remind you of some things. So concerning functions, and their combinations. Combinations, yeah, like that. So now here's something about numbers, is that you can take two numbers and you can combine them to get another number. Okay, and one way to do that is with add. You know, you could take two numbers and add them and get another number. You could take two numbers and subtract them and get a number. You can another one. You know, you can take two numbers and multiply them and get another number. You can take two numbers and divide them and almost always get another number. So now I have to say, you know, I have to hedge a little bit and say almost always. So why? Yeah, because you can't divide by 0, right? So concerning so concerning numbers, you can add, subtract, multiply, and divide them. And you can do other things like raise one, make one the exponent of the other. You can do there's other things, but add, subtract, multiply, and divide. Now you can do all those things with functions in the following way. You can say that we can say let f and g be functions. Like that, and then we can say that we will define the following, that we want to say f plus g. So that's a thing, right? So f plus g are functions, and understand that in this class, whenever we say functions, we mean to say that they have signature reals to reals. So they accept a real input and produce a real output. So we want to make a new function, f plus g. It will have the same signature, because it needs to have the same kind of thing. It needs to be the same kind of object as each one of these, right? The thing on the left is a function of signature reals to reals. The thing on the right is a function of signature reals to reals. So the combination should be a function of signature reals to reals. So we'll define this by saying that, well, if you took f plus g and you wanted to evaluate it at x, so that means take that thing and then you want to evaluate it at x, the way you do it is you say, well, first I'll evaluate the f at x, and then I'll set that aside, and then I'll take g and evaluate it at x and set that aside. And now that I have both of those, each one of the pieces evaluated at x, what do I do with the results? You add them together. Okay, not surprising, right? So can we agree that I could replace the plus with the minus and it'd all be the same? And if I replaced it with the multiply, it'd all be the same? Okay, so concerning numbers, you can add, subtract, multiply, divide them, and some other things. Concerning functions, you can do those same things. But functions have something that they can do that numbers can't do. And it's an operation, like plus and subtract, and all those are operations. So what's the thing that functions can do that numbers can't? I'm fishing for a C word. They can compose, right? So we can define, what I'm saying is that we can define this in a similar way that I won't bother writing, this in a similar way that I won't bother writing, this in a similar way that I won't bother writing. And finally, here's the new one, the one that functions do that numbers don't. Okay, so composing two functions, we'll define this by f composed with g evaluated at x. So now all of these ones, all of these first four, they're just like this one. which is to say there's two functions. So first I'm going to evaluate the one on the left at x, then I'm going to evaluate the one on the right at x, and then I'm going to add or subtract or multiply or divide. So you do those things separately. This one at x, that one at x. Compose is different. How is compose different? Right. So the definition is that you take g, you evaluate it at x. And then once you've evaluated g at x, what do you do?
F at g.
Now you take that value and you plug that thing into f. Like so. Ah, that's different. Now I want to make sure you understand the difference. Is that, if you wanted to, if you had a function that, and you represented them as like boxes. So like x is going to go into the f box, and then out comes, the way that we name it is f of x. So you put an x into the f box, out comes f of x. You put an x into the g box, and then out comes a g of x. Okay, so having that kind of idea, so if we put in a theta, out would come g of theta. Okay, so having that kind of idea, the sum, the add, subtract, multiply, and divide, they all look like this. And what I want you to imagine, a good physical analogy for functions is an assembly line, like a process. So suppose that we want to consider how does f plus g look? How does the f plus g function look? Well, what it does is this: it says, okay, we'll take the x, and now we've got a big box here. Okay, and then what we do is we make 2 copies of the x, and we send one to the f machine, and we send another one to the g machine. Okay, then out comes f of x from this one, and out comes g of x from this one. So in principle, these things can be done at the same time, right? Then we take these two outputs and we combine them with an addition. Okay, so we combine them with an add, and then out comes on the other side f of x plus g of x. So this diagram is what f plus g is. Okay, and there's nothing sacred about plus. I could draw exactly this diagram with subtract, multiply, or divide. So, it's like, concerning like an assembly line, here is a fork. There's a fork in the road, right? You go things go different ways. Concerning composition, it looks like this. You take the x, and written in this order, we're going to visit, just like both the f machine and the g machine were visited, we're still going to visit the f machine and the g machine, but which one's going to be visited first? The g machine is visited first. So it goes into the g machine, and out comes a g of x. And then, now that itself goes to the f machine, and out comes f of g of x. Now, covering all this up in a big box, the name of that big box is what? F composed with G. That's what it is. So now, these commute. The adds, well, add and multiply commute. Subtract and division don't. They have a different property called, like, depending on who you're talking to, anti-commute. But these commute, which means that it doesn't matter what order these occur in. Like maybe you do the f thing first, maybe you do the g thing first, maybe you do it at the same time, doesn't matter. Whereas these don't. G must occur first and then f. The way you can understand that, again, with the assembly line analogy, is to imagine, what if we all said, forget this calculus, let's go start a business. And, let's start a doll making business. You can imagine that you've got dolls, and then they have like clothes on them and stuff. Like just going to Toys R Us, you see a doll there. You can imagine that we've got like a station that puts on the various items of clothes. Okay, so you can imagine that we have like a left shoe putter on her station, and we've got a right shoe putter on her station. Does it matter what order those stations are in where the final product is concerned? No, it doesn't matter. You wouldn't be able to inspect it and say, I see that the left shoe was put on first. You wouldn't be able to tell. Whereas if we have a left sock putter on machine and a left shoe putter on machine, does it matter? Sure it does, right? Or, in a slightly more funny way to say, what about the pants machine and the underwear machine? Does it matter what order those are in? Sure, right? One of them is Superman, right? And the other one is Ken, I guess. I don't know. Barbie's companion. All right, so composition does not commute. First that one, then that one. Now the rules that you learned in differential calculus, are like the sum rule. They're saying that what if you have an F machine and a G machine, and moreover, the derivative of the F machine and the derivative of the G machine, then what is the derivative of the combined F plus G machine? That's the add rule, the sum rule. When you're doing the corresponding thing, if you have a composition like this, and the derivative of the G machine, and the derivative of the F machine, then what is the name of the rule that tells you the derivative of the composed F with G machine? What's the name of that? That's the chain rule. Because you can kind of say these functions are chained together. First that one, then that one. The chain rule is telling you, what happens. So the chain rule is this. It's saying that suppose that we're given F and G, both with signature reals to reals, and we know the corresponding derivative functions, F prime and G prime. So we know we've got two functions, and moreover, we know their derivatives. Then the question is that what is the formula for the derivative of the composition? Okay, so you could write it like this. The derivative of F composed with G evaluated at X, like that. Okay, so that's the question we want to answer. And usually in your textbook, at the 2000 level where we are, it's probably written like this instead of with the composition operator. It's probably written that way. So the way that you do this is well, you just look at the machine. So X visits G first. So the first thing we've got to do is we've got to calculate the derivative of G. So we're going to have to calculate the derivative of G, so G prime. And then after that, it visits F. So we're going to have to, do the derivative at F also. Like that. So we've got the derivative of F, and we've got the derivative of G, and you can sort of consider them a little bit separate. How are we supposed to combine them? Are we supposed to add them? No. What are we supposed to do? We're supposed to multiply them. You multiply them, and the final thing you have to ask yourself is that where are each of those derivatives supposed to be evaluated? Well, have a look at the machine. Where is G evaluated? At what is the input? It's evaluated at X, right? So you have to take G's derivative and evaluate it at X. Does that mean we should also evaluate F's derivative at X? But we evaluated G's derivative at X.
But F is taking G of X.
Right. So consider here, what is the input to the F machine? Is the input to the F machine X? No, it's G of X. So the derivative of F has to be evaluated there. So that's the chain rule. You've got two functions composed. What you do is you take, if there were 10 functions composed, okay, you'd take all the derivatives, multiply them all together, and you just have to keep track of where is each one evaluated. Right? This one there, that one there, that one there, all the way down the line.
So derivative is the derivative of the inside, which is in this case g of x multiplied by the derivative of g of x.
Right, but you know what I'm saying is that if it looked like this instead, if it was you know, something like first we go to the A machine, so that's an A, out comes A of x. Then we go to the B machine, out comes B of A of x. Then we go to the C machine, if you like. Out comes C of B of A of x. Then the chain rule is saying, the chain rule, the derivative of this chain of functions, right? Okay, is, you would say, okay, we'll need to evaluate, you know, you have to do it in the correct order. What order do I have it in? C comes last. So C needs to be all the way to the left. So it would be C's derivative evaluated somewhere, B's derivative evaluated somewhere, A's derivative evaluated somewhere. And then what do we do with all those derivatives? Do we add them all together? No, we multiply them together. And then now the question is where does each one get evaluated? So have a look at the machine. Where does A get evaluated? At x. Where does B get evaluated? At A of x. And where does C get evaluated? B of A of x. Okay? Now, the reason you could reasonably ask, why multiplied? Why multiply? So in some sense, I could just say, well, I could just like derive it for you, and I hope your calculus instructor did it. But rather than repeat that that calculation, I want to kind of give you an intuition for why it simply must be multiply. So here's a nice thing that we learned like in the last couple hundred years, and that is that you know, when people get sick, it's not because of magic or vengeance or anything like that. It's actually because of little creatures that are trying to kill us and eat us, you know, because we're their food. You know, bacteria and things like that. And the reason why, one of the reasons, among the reasons why we didn't realize that is we couldn't see them. They're so small. How is it that we see them? You use a microscope. So I hope you've all taken a biology class. So the way microscope works, right, you put your eye right up there. And I remember in biology class, I always tried to like keep my distance, you know, because who knows how many other people put their eyeball right up on there, okay? But fine, you look right up on that, you get your eye right up to that thing. What's the name of that first thing you're looking at? That piece that your eye, right there. The eyepiece. That's what it's called, okay? Then you get the goo that you want to look at, and it's sitting on top of that flat bit. That's called the table or the stage. And then you rotate the thing, you know the rotating thing, where you can select the magnification that you want. What's that one called? It's an O word. Starts with O, ends with bijective. Objective, yeah, I found it, okay. So then that's the objective, right? So here's the thing, is that the eyepiece is a magnifying lens, and so is the objective. The objective usually you can select through choices that are something like, you know, like 20, 40, and 50, or I have no idea. That's not my thing. But you can make a selection. So suppose that the eyepiece has magnification 10, and you have set the objective to 40 magnification. Then what's the total magnification? 400. It's 400. Notably, it's not 50. It's not 10 plus 40. It's 10 multiplied by 40. The reason is because what's happening is that you've got the goo right here that you want to look at. Okay? Then you've got a light source. And all that a light source is a bunch of photons streaming out. Okay? They're all coming out. They pass through the goo. Okay? They go into the objective. And what's happening is that these are mostly photons going straight into the objective lens. And that lens, what it does is it takes those photons and it causes them to spread out by a factor of 40. It opens them up. It takes these lines and does that. So now, many of them many of these things diverge and end up hitting the neck of the scope, and they're like lost. You know, they're gone. But many of them travel up here to the eyepiece. You know, many of them make it, and then the eyepiece takes those lines and makes them spread out even more by a further factor of 10. So what's happening is that by the time they get from here to here, the photons are, you could think of it like they're 40 times further apart than they were. Okay? And by the time they pass through the eyepiece, those ones that went in are now 10 times further apart than they were. So how far apart are they? 400 times. One lens composed with another lens. Not 40 plus 10, 40 multiplied by 10. Not this one plus that one. This one multiplied by that one. That's one. Good. Now, that being the case, what I did, and the thing that I did, and then I got a lot of blank looks, but I couldn't stop and deal with it because I had time pressing against me, is I wrote this. The derivative of, antiderivative of exponential of 3t dt. And I wrote this without apology, quickly, and then I got a lot of looks of like fear. So that's something that should be just, very straightforward. Now the reason why is because if you look at the chain rule is saying, essentially, that, like here's an example. The derivative with respect to x of e to x. Now this is something that you must know. What is it? It's exponential of x. No, derivative. Derivative. So exponential, in fact, you could put any constant you want there, like a k. So k, which one is it? This one. This one? No. Okay, I'm going to just turn it off and turn it back on. It's coming. All right. So, come on now. Okay, so then the derivative of exponential is itself. Okay, so now in a sense, from like a really superficial point of view, what the chain rule is saying, all the chain rule is saying is that here's a rule that you know. If these are in agreement, that and that, then that's the answer. Now, what if these are not in agreement? What I mean to say is, notice that this is an x and that is not an x. It's a w. So what we're saying is that, w, you can imagine that w is some kind of name for something that we're going to do to x before it gets to the exponential. Like, haha, I'm going to play with the x before you get it, exponential. So w is coming before x. So these two things are being composed. So if that were exactly an x, what would the answer be? Right. And so if those were in agreement, that would be the answer. If. But they're not. That's a w. So as a result, to satisfy the chain rule, we need to say that, in fact, this needs to be multiplied by the derivative of w with respect to x. Because we have to account for whatever it was that w did before the exponential got a hold of it. Now, if the world is just, we should be able to say that this is up here, right? So now I'm gonna move this dw dx up here. So if I want to do that, then what do I need to write right here? Do I write dw dx? What do I write? I write dx dx, right? But wait, what's dx dx? It's 1. It's always been there. It's always been there. As a result, if you do something like this, derivative with respect to x of exponential of, say, 5x, like that. So what I want you to observe is that this says x, and that says 5x. So are those identical? No, they're not. What it's saying is that you know, you're like playing a joke on the exponential. You're saying, haha, before you get the x, I'm going to multiply it by 5. And then you get it. Right? So the multiply by 5 machine receives it first, and then that's given to the exponential. So just covering this up, just covering that up, okay, if that were exactly an x, then the answer would be exponential of 5x. If it were exactly an x, but it's not. So what we have to do is we have to say, well, how did that multiplication by 5 end up affecting the whole process? Well, the way it affected it is codified by the chain rule. So you have to include multiplication by the derivative of 5x. What is the derivative of 5x? It's 5. So you have to write 5 here. Okay, and if you feel really strongly compelled, you can write the 5 in the front. But I'm always going to write the 5 in this case, always on the right. Okay, finally, antiderivative. Okay, the derivative itself is a machine, just in the same way we're talking about these functions. If you take this thing and put it in this thing, if you put this thing into that thing, out comes this thing. Okay, derivative is a machine, a function. So all that this is saying right here, this is saying the following, is that you know, we're running the derivative but in reverse, antiderivative. If you were differentiating just that you can see between my fingers there, what would the answer be with respect to t? Exponential of 3t multiplied by 3 for the chain rule. So you follow it up with a multiply by 3 because that's what the chain rule says. So the chain rule says multiply by 3. What about the anti-chain? What about the anti-chain rule? Divide by 3. So the exponential of, say, 5x, like that, antiderivative. Okay. Now, are these in agreement? This x and this 5x, are they in agreement? They're not. What I mean is, are they identical? Are they exactly the same thing? They're not. So what we're saying is like, okay, that's an x. We're doing it with respect to x, but this 5x is playing a game. You know, like, haha, I multiplied by 5 before you got it. Now deal with it, haha. Okay, well, if that were exactly an x, what would the answer be? It'd be exponential of, right. It would be this. Okay? But now, to satisfy the chain rule, but in the opposite direction, we're not going to multiply by 5. We're going to divide by 5. Is it clear? Good. So now, there's nothing special about exponential. Okay? Well, I'll say it like this. What if it was like cosine of, say, 7 theta, d theta? If you wanted to do this. So in the first place, what is the antiderivative of cosine of x dx? Sine of x. Now, are those two the same thing? Is theta the same thing as 7 theta? No. So, but suspending that for a moment and just imagining if they were, then the answer would be sine of 7 theta plus a constant, if those were the same. But they're not. So if we were differentiating that to satisfy the chain rule, we'd have to multiply by 7. Because we're anti-differentiating it, we won't multiply by 7, we will divide by 7. Good. Any questions about that? Okay. I hope that the matter is clearer. I'm getting much happier faces now. I feel better to proceed. Good. So now concerning trig integrals, okay, which is and antiderivatives, is we want to do stuff that involves crazy combinations of trig functions. Okay, so here we go. This is section 7.2. So we can just do it by example, I think. So in the first place, you must know that the antiderivatives of all the various trig functions. So like antiderivative of cosine is sine, antiderivative of sine is negative cosine, etc. What about did y'all do like antiderivative of tangent? Yeah? No? Antiderivative of secant? Yeah, I wish I was part of the 2413 thing. They just threw me in here. Okay, so we'll do it like this. Suppose I ask you about say this one, sine, antiderivative of sine of we'll do this of 3 theta, like that, and then we're going to raise it to the 5th power, like that. Okay. So now, in fact, we've got a composition of 3 things. Okay. The reason why we have a composition of 3 things is that we take the theta, we multiply it by 3. Haha, now you get it sine. Okay, then you sine it. You know, you do that, and then you give it to the raised to 5th exponent machine. So there's this one, that one, that one. Okay. So all right, the way that we're going to deal with this, and the main trick here, is that we need to know 2 things. In the first place, this exponent is odd, as in not strange, but as in not even. It's odd, and furthermore, here's information that you're required to know. So the cosine of x, you square that, plus the sine of x, you square that, is equal to what?
1.
It's equal to 1. And so that we can refer to this by name, what is the name of this? What's its name? Ah, I see that we don't know it. This is called the Pythagorean identity. It's called the Pythagorean identity because if you draw a unit circle and select whatever point you care to choose, then from the origin that forms a right triangle. The height of that right triangle is sine. The base is cosine. So if it's on the unit circle, you square the base, you square the height. That's got to be the hypotenuse squared, right? And if it's the unit circle, it's got to be 1. So it's called the Pythagorean identity. So here's the trick. We have an odd number of sines. Okay, so what we're going to do is we're going to save off 2 of them. We're going to do this. So we're going to save off 2 of them, and then there would be 3 more. So like this. And now that we have those 2, we can convert those 2 into cosines, right? Using this one, right? Okay. So like that, and so this would be what do I need to write in here to make it right? For what? So specifically, what I'm asking is I'm going to write this. And what I'm asking is that what is it that I write in those square parentheses there?
1 minus cos x squared.
Right, 1 minus cosine squared. So 1 minus cosine 3 theta squared. And now we're going to do the trick one more time. And then you would normally, when you understand how this is going to work, you would just do it all in one step. But notice that we still have three of these, right? This one, that one, that one. So now I'm going to take another 2, and I'm gonna do the same, so that it looks like this. So antiderivative, so that one is still there. So cosine of 3 theta squared, and then now I'll peel off another 2 in another set of square parentheses like this. So I took 2 more sines and converted them to cosines like that. So how many sines do we have left?
1.
Just the 1 there. So it looks like this. And, you know, of course, when you get accustomed to doing this, you would probably more or less come to like this step pretty rapidly. You just say 1 minus cosine of 3 theta squared. In the square parentheses, I'll square those, multiplied by sine of 3 theta d theta. And now I claim that we're in pretty good position. Why?
We cannot use a U and V.
Yeah, well, you mean the product rule? Well, it might be possible to do that, but there's a much easier game. And someone said it. A U-sub, right? A U-substitution. The reason is because, have a look. Anytime that you see something that looks like this, that looks like thing multiply by other thing, remember what the chain rule is saying. The chain rule is saying that you evaluate this thing, this derivative, and you evaluate that derivative, and you evaluate this one at that point, and that one at that other point, and then you multiply them together. So anytime you see something like that, you should have the idea that, oh wait, maybe the chain rule was here. Like if you can imagine personifying the chain rule and the chain rule like scrawling on the wall like chain rule was here. What I'm saying is that this smells like chain rule. Okay? If this right here is the thing that chain rule left behind, if this is the derivative of something, if this is du, then what's u? Cosine something or other, because sine is the derivative of cosine looks like sine. Okay? Of course, there's a negative in there somewhere. So if we say that u is cosine of 3 theta, if we say that, then what's du?
4 minus. No.
As I ignore all this, so what's the derivative of cosine? What's the derivative of cosine? Negative sine of 3 theta multiplied by 3. Why multiply by 3? Chain rule, right? And is this correct as written? D theta. So again, the reason why this is not correct as written is because what these things are, these are called forms. Now we don't really talk about that in this class, but I like to say it because it helps you understand how to calculate. Now because there's a single D thingy over here, that means that the left-hand side presently as written is a 1 form. And how many D thingies are on the right?
0.
None, presently. As a result, what you're saying is this 1 form is equal to that 0 form. That's nonsense. Okay? That's like apple and banana. It's not the same kind of thing. So it's not permitted to omit the d theta. Now there's some extra junk here that we need to handle. So this we want to be the differential bit, but there's not a negative here. There's not a 3 here, an extra 3 here hanging out. So I'm going to move that stuff over there and say that du divided by negative 3 is sine 3 theta d theta. Any question about this? So what I'm advocating here is I'm saying that all of this bit is going to get replaced with that. And similarly, this is going to replace that. Okay? So this is called a change of variables, or if you like, a substitution. But better is to call it a variable differential substitution, because so the variable is theta, the differential is d theta. So notice that I've covered up a bunch of stuff. Like I covered up the cosine 3 theta, and I covered up all that, but I didn't cover up the 2. You know, what about that 2? Do we need to substitute something for the 2?
No.
Why not? So what's the name of this technique? It's called a U-substitution, but I really wish it was not called that. Okay. So later, if you go take on further math classes, it'll be called a change of variables. So that's a little bit better name, but probably, well, at least in my opinion, the best possible name is this is referred to as a variable differential substitution. And the reason why that's a good name is because it's telling you what needs to be handled. So, is theta a variable? Yes. That's why, are there any thetas that are not covered? No, they're all covered, right? What's the differential? The d theta. Now, concerning that 2, is that 2 a variable? No. Is that 2 a differential? No. So it need not have any, it need not take part in the substitution, right? Good. So let's write this down. So the resulting antiderivative would be 1 minus u squared, square that, and then du. No, not du. Du over negative 3. All right. So the division by negative 3 can be factored out. Supposing we do that, how do we deal with this? Sorry?
A square minus b square formula. I don't know what that would
Okay. So negative a third multiplied by this. So let me get that negative third out of the way here. So the question is, what do we do with this? Okay, so I have a question for you. So y'all taken a math class before this, right? So, you know, considering your personal history, did you do arithmetic first or algebra first? Come now. You know, like in first grade when you're learning how to do, like, add? Yeah, you did arithmetic first, right? And you've taken differential calculus. Did you do algebra first or differential calculus first? Oh, you did algebra first? Good. That's the way it goes. So now, generally speaking, the reason why I'm telling you this story is that when you're doing a math problem, it is a very good idea to perform all of the algebraic steps first before you do any calculus stuff. So what? We have to multiply this out. You can't do anything else. There's no other way to proceed. Algebra first. So that is to say that you multiply this out and you get 1 minus 2 multiplied by u squared plus u to exponent 4, then du. Now each one of those terms, we can use the power rule, right? So then the answer would be negative a third multiplied by, so what's the antiderivative of that? Just u. And then subtract, the antiderivative of that would be 2/3 u cubed. And then the next one, a fifth u to 5. And then plus c. Now is this the answer to the question? No, it is not. Why not? Right, because the question was phrased in terms of the variable theta. Presently, the answer is phrased in terms of u, so it's not correct until you put it back in terms of the original symbol, theta. So that'd be negative a third, and then what is it? Cosine. So cosine of 3 theta subtract 2/3 multiplied by cosine of 3 theta cubed, and then add a fifth multiplied by cosine of 3 theta to exponent 5, and then all of that plus c. Any question about this one? So now, this trick will work when you have a product of sines and cosines where either the exponent of the sines or the cosines is odd. So like you could do it with like you could do like cosine to 20, to exponent 2413 multiplied by sine to exponent 2414. Now, because one of them is odd, you'd be able to use a version of this trick. Okay? So that raises the question, well, what if they're all even? Yeah? Very good. So here's such an example. So antiderivative of, we'll start with the simplest one. How about sine of twice theta, and now we're going to square it. So now what I want you to see is that the trick won't work, because how many sines are there? 2 of them, right? Because it's this one and that one again. How many cosines are there? 0. And is 0 even or odd? It's even. If I gave you 8 M&Ms and I put them in front of you and said, please make groups of size 2, how many groups could you make? How many would be left over when you've done that? 0. The fact that there are 0 left over is why 8 is even. If I put 11 M&Ms in front of you and said, make groups of size 2, how many groups of size 2 could you make? 5. How many would be left over? 1. The fact that there's 1 left over is why 11 is odd. Now, here's a surprise. I have put 0 M&Ms in front of you. Now I want you to take those M&Ms and make groups of size 2. Please do it, and let me know when you're done. Got it? Now that you've done that, how many are left over? The fact that there are 0 left over means that 0 is even. So there's an even number of sines and there's an even number of cosines. So there's not an odd number of any one of them. So we can't use the previous trick, and we must do what he said. Here's something that you must now commit to memory if you hadn't already, is that the sine of x squared, there's a formula for that, and cosine of x squared, there's a formula for that. Can y'all see that red? It's kind of faint. Okay, so they both, surprisingly, at least until you think about the formula, look very similar, the formulas. So you got a 1 here, you've got a cosine of twice x here, and then this is all over 2. You've got a 1 here, you've got, again, a cosine of twice x, and then all over 2. So far, I just wrote exactly the same thing. I'm trying to find a spot where you can see it. Can y'all see that?
Yeah. Yep.
So the question is that in that slot between the 1 and the cosine twice x, they're both the same, what am I supposed to write? I agree that 1 is plus and 1 is minus.
First one is minus.
This one, the one with sine is minus, and the one with cosine is plus. In the end, you should look it up carefully, but in the end, the reason has to do with the fact that cosine is an even function and sine is an odd function. So if you take a negative value and raise it to an even power, the result is positive, right? And if you take a negative value and raise it to an odd power, the result is negative. That more or less is the reason why they are this way. So finally, can you see that, we could do that. Now the virtue of this formula is that, notice that this expression is a composition of sine and squaring. And composition is difficult to deal with antiderivatives. It's always like a battle. You're trying to undo the chain rule. So this is a composition. Now this also is a composition because it's a composition of multiplying by 2 and cosine. But that composition is easy to deal with. So that's why you want to do this with antiderivatives. So what I'm saying is that we can reduce this thing in some way. So now I'm going to write something, and it's not right. It's not correct. So it'll be 1 and then all over 2, and then subtract. I remember that much. So then now sine, and then I remember the 2, so I'm going to write 2 theta. There we go. Good. D theta. Something's not right. Oh, okay, there's more. Sorry. So okay, yeah, that one was not intended. Sorry. Yes, it should be cosine because they're both cosine. Okay.
2 times 2 theta.
That's what I wrote, 2 theta.
Well, but 2 multiply that by 2 again because the formula is 1 minus cosine 2x.
That just means
Very good. Reducing this power comes at the cost of doubling the angle. So presently the angle is twice theta. If you double it, it must be 4. So now then, because we're more or less out of time, I'll simplify this quickly and say that this is half, like that, and then subtract half multiplied by cosine 4 theta, like so. Now each one of these you should be able to do very straightforwardly. So for example, antiderivative of half is half theta, and then subtract half. And now, what is the antiderivative of cosine 4 theta? Whose derivative is cosine? Sine. So it'll be sine, and it will be evaluated at 4 theta. Now, if it were exactly theta, we could stop, but it's 4 theta. If we were differentiating for the chain rule, we'd have to do what? You'd have to multiply by 4. But we're anti-differentiating, so it's not multiply by 4, it is divide by 4 at a constant. Okay, so what this is an example of is that when you're anti-differentiating a product of sines and cosines, and they're all to even powers. So you could imagine like cosine to exponent 8 multiplied by sine to exponent 10, and they both have to have the same argument. So they could both be 4 theta, they could both be whatever. You have to repeatedly use these rules. Okay, until maybe if you can swing it, somehow get to an odd number of them, and then you can start using the other rule. Okay, good. I hope you have a wonderful Friday.